In this video, we will discuss the Fourier transform. We have already derived the equations and we have already discussed the Fourier series. But in this lecture, we will discuss what is the Fourier transform. Basically, you use Fourier transform in order to calculate the frequency component in a signal. Like you can say that if you want to transform the time domain signal into the frequency domain signal, then you can use Fourier transform. Like both Fourier series and Fourier transform are the mathematical tools for representing signal in frequency domain. Fourier series is mainly used for the periodic signal, whereas the Fourier transform is used for the aperiodic signal. That is the basic difference between the Fourier series and the Fourier transform, because both tools are used for calculating the frequency component in the signal. But you know that the Fourier series is basically used to calculate the frequency components if the signal is periodic. But if the signal is aperiodic, non-periodic signal, then you have to use Fourier transform. So in order to calculate the frequency component, you need to transform the signal into the frequency domain. If you want to use the Fourier transform, then you have to consider the condition for the Fourier transform. So that is the condition for the existence. Like function should be absolutely integrable. Like integrable mean that if you take the integration of the given function, then it should be less than the infinity. Like in another sense, you can say that if you take the integration of the function, then it should give you the finite value. So if the integration has a finite value, then you can take the Fourier transform. Second condition is that function must have a finite number of maxima and minima. Like if in an ideal case, a sine wave is given or a cosine wave is given, then you can easily calculate what is the maximum value or what is the minimum value in that function. But if you take the example of a noise, so you don't know how many maxima or how many minima are there in that noise. So, but the condition is that function must have finite number of maxima and minima. The third condition is that function must have a finite number of discontinuities. Discontinuity means irregularities. Like if a function have a finite number of irregularity or disconnection, then you can say that you can take the Fourier transform. But if the function has an infinite number of discontinuity, then you cannot take the Fourier transform. So like in order to take the Fourier transform or in order to apply the Fourier transform over a signal, the signal should fulfill these three conditions. Deriving Fourier transform from the Fourier series. Like you can derive the Fourier transform by using the Fourier series. We have already derived the formula for the Fourier series, that is x of t is equals to summation, where k varies from minus infinity to infinity. X of k e raised to power j k omega t, where x of k is the coefficient of approximation. We considered the coefficient of approximation in our previous lecture with the symbol f of n, but you can even consider f of k. You can consider either x of k, so it doesn't make any difference. Like you are using different symbol for the coefficient of approximation. So in this case, you have considered the coefficient of approximation is x of k. So let's consider some basic points. We know that the angular frequency omega is equals to 2 pi. So you can replace this omega in this signal, like omega is replaced by 2 pi by t. So similarly, the coefficient for the equation, like you can say that let's del of t is equals to 1 of t. Why del of t? Because we know that the Fourier transform is used for aperiodic signal. Usually for the periodic signal, we know that f is equals to 1 over t. But in case of aperiodic signal, you can write del of f is equals to 1 over t. So then you can replace 1 over t in this equation with this del of f. So and then you can say that this is equation number 1. Equation for the coefficient, like this coefficient of approximation, you already draw this equation for this coefficient in our previous lecture, which is equals to 1 over t integral, where the lower limit is t naught and the upper limit is t naught, plus capital T x t e raised to the power minus j k omega t dt, which can be written using these assumptions like del of f and omega is equals to 2 pi by t, so which is equals to 1 over t and then integration x of t e raised to minus j k 2 pi del of f t dt. Putting the value of the coefficient of approximation, like you can insert this value in this equation. Equation number 1, x of k. So use this value in this x of k, and then you will end up with these equations. So like x of t is equal to summation del of f integration x of t e raised to minus j k 2 pi del of f t dt multiplied by e raised to j k 2 pi del f t. So let's consider that t naught is equals to minus t by 2 in this equation. So if you consider t naught is equals to minus t by 2, then lower limit is replaced by minus t by 2, upper limit is replaced by t by 2. So then the same equation can be written by having different limit value, like from minus t by 2 to t by 2. To consider the limit t is equals tending to infinity for the Fourier transform, and then in that case you can replace the summation sign with the integration, you can replace del f with the df, you can replace k del f with the f for a continuous signal, like x of t, you can replace all those considerations, then you can say that del of f is replaced with df, summation is replaced with the integration from minus infinity to infinity. Similarly here the integration is replaced with the minus infinity to infinity, because if you insert t to infinity, like if you insert t to infinity, so minus t by 2 it will be equals to infinity, and capital T by 2 is equals to infinity, and the remaining equation is same as it is. Like here you are replacing del of f with f, okay, so dt and then e raised to power j 2 pi f t, and you are replacing k del f with single f. Then the simplified form is written in this case, x of t is equals to 1 over 2 pi x omega e raised to power j omega d omega. And you know what is x omega, which is equals to x of t e raised to power minus j omega t. Why this is 1 over 2 pi? Because we are converting from f domain, f, we are converting f into omega, and we know omega is equals to 2 pi f, and d omega will be equals to 2 pi d of f. So it means that you are just simply replacing that df with the d omega. So if you replace this df with the d omega, then df will be equals to 1 over 2 pi d omega. Okay, so that is why you are ending up with this equation, and then you are ending up with this coefficient x of omega is equals to x t e raised to minus j omega t. So this means that if you want to take the inverse Fourier transform, then you will use this formula, and if you want to take the Fourier transform, then you will use this formula.